Hello everyone, my name is Lisa Dang and welcome to my poster. So today I'm here to present the analysis of the thermal phase curve of the eccentric hot Jupiter EXO3b. So EXO3b is an 11 Jupiter mass gas giant hosted by an F-star on an orbit with an eccentricity of about 0.3 and an orbital period of over 3 days. Here is a top view of the orbit of the planet, where the occultation, periapse, and apoapse are labeled to get a general idea of the geometric view of the system. And the planet here is orbiting counterclockwise. So here is an overview of what we can learn from the phase curve of hot Jupiters and how it's different for hot Jupiters on circular orbits and eccentric orbits. So for hot Jupiter on circular orbits, they receive a constant amount of stellar flux, and they are thought to be synchronously rotating, which means that if we observe a full orbit phase curve, we can get a longitudinal brightness profile for the planet and insights on how effectively the atmosphere of the planet is redistributing heat all across the planet. For planets on an eccentric orbit, they are not tidally locked, but they experience what we call pseudosynchronism. So the planet is only tidally locked near periapse, where momentarily one side of the planet gets flash heated, and then for the rest of the orbit, it will spin around on its axis and experience days. They also receive a varying amount of stellar flux across the orbit because the distance between the planet and the star is varying. And fun fact, EXO3b receives 3.3 times more stellar flux at periapse than it does at apoapse. This varying stellar flux, however, allows us to break the degeneracies between the radiative and advective properties of the planet's atmosphere. So, we observed EXO3b continuously as it completed a full orbit with the Spitzer Space Telescope in the 3.6 and 4.5 micron bands. We reduced and analyzed the data using an open-source, fully automated Spitzer phase curve analysis pipeline called SPCA, developed by Taylor Bell and I, which can be accessed right here by clicking on this link. The best fits are shown up here in the middle. But before getting these, we experimented with various decorrelation methods, namely polynomials, Bliss mapping, and pixel level decorrelation. Below is a subset of all the different fits that we obtain using different decorrelation techniques and models and priors. So what I want you to notice here is that the background color for each of these fits is proportional to the goodness of the fit. And so this is the metric that we use in order to select the best model. Finally, we used a Gaussian process regression to obtain an apparent effective temperature curve based on the Spitzer phase curves right here. This is shown in green right here, and the swaths represent the uncertainty on this temperature curve. Then we are going to fit this curve using an energy balance model, which as fittable parameters has P0, the pressure at which the stellar energy is being deposited, the equatorial wind speed of the planet, its Bon albedo, and any amount of internal heat it may have. All of this is still a work in progress, so the curve that is overplotted here is preliminary results, but we are going to have to do a more thorough parameter space in order to get better constraints on these parameters, but also to see if there are any degeneracies. Then we can use the estimates for these parameters to then estimate the radiative and advective timescale of the planet. So thank you very much for coming to my poster, and if you have any questions, feel free to message me on Slack.